Welcome students to a new lecture video. Today we will discuss the concept of torsion of a cylinder and then we will derive an expression for the torsional couple. So in the previous lecture videos we have discussed the Young's modulus of a material, how to calculate the Young's modulus, and what are the expressions for the depression as well as the elevation of loaded beams. Now, in this section, we will be discussing primarily about the rigidity modulus. So, we all know that rigidity modulus comes into play when there is a change in shape of the material or shape of the object and there is no change in the size of the object. If you have a cylindrical rod or wire which is tightly fixed at one end, say for example, you have this is the fixed portion and you have a cylindrical wire like this. So assume that you have a cylindrical wire like this and you are going to twist this wire. That means you are going to apply a force in this direction to the free end. Okay, so you are going to apply a force like this. That means you are twisting the wire. So you are applying an external couple and due to the effect of that external couple, this wire or the cylinder fixed at one end will undergo a twisting. So during the twist, there is a change in the shape of the body and so we are considering rigidity modulus alone. So there is no other change to the dimensions. That means a length is not changing, its thickness or the radius, nothing is changing. So you cannot take the concept of Young's modulus here. Only the concept of rigidity modulus can be taken into account because the only thing that changes here is the shape. Okay, and I hope that you remember that is if you have a rectangular rectangular shaped material and if you apply a tangential force at the top of the material, it will get converted into a parallelogram. So a rectangle changing into a parallelogram, and that is what we mean by saying a change in the shape of the material. So having said this, now we will go on to the derivation, that is how can you derive an expression for the torsional couple of a wire or a cylinder which is fixed at one end, that is usually it is fixed at the top and a twisting force is applied at its bottom. So as you can see from the figure, you can see three figures. We will explain it one by one. So the first one is a cylinder. Okay, so you have a cylinder here and assume that the length of the cylinder is say L. So this is the length of the cylinder. So capital L will give you the length L of the cylinder and the radius of the cylinder is small r. So you can see that small r in the second figure. Okay, so here you can see the small r. See, the second figure is nothing but the top view of the cylinder. So this is figure number 1, this is figure number 2 and this is figure number 3. Okay, so figure number 2 is nothing but the top view of figure number 1. And then you will be able to see the cylindrical base of the cylinder. Okay, and R is the radius of the cylinder. Now, the upper edge or the upper end of the cylinder, that is say this portion, So this is the upper portion of the cylinder, and this portion is rigidly clamped, and a twisting couple is applied at its lower end. So here you are applying a couple, a twisting couple in this direction. When the rod starts twisting, a restoring couple is developed inside it due to elasticity. That means when you remove the twisting couple, the rod has to come back to its original position. So there has to be a restoring couple which brings the rod back to its original position. So this restoring couple will be acting in a direction opposite to the twisting couple, and we know that when the rod is in equilibrium, the restoring couple and the twisting couple, they equals to each other. Okay, or these two forces balance. When these two equal and opposite forces balance each other, we say the cylinder is in equilibrium. Okay, so now our duty is to derive an expression for this couple. Okay, so what you are going to assume is you are going to assume a cylinder, that is say figure number 1, which is made up of a large number of thin coaxial cylindrical shells. So now let us assume that you have a coaxial cylinder. That means large number of cylinders having the same axis. Okay, so you have a large number of coaxial thin cylindrical shells, and in fact it is to be noted that the whole cylinder is made up of large number of these coaxial thin cylindrical shells packed very closely. Coaxial means all the cylinders are having, or all the cylindrical shells are having the same axis. Okay, and we assume that the radii of these cylindrical shells, it starts from 0 and goes up to R, because R 0 is the midpoint, and R in the second figure you can see I have circled R. This R is the total radius of the cylinder. So all the other cylinders, all the other thin cylindrical coaxial shells will be lying between 0 and R. Okay. Now you can see a line AB here. See, A at the top and B at the bottom. So before twisting, this AB is parallel to the axis OO dash. But when you apply a twisting couple, that is F, as shown in the figure, the cylinder will twist. The cylinder undergoes a twist, and as a result of that twist, now AB, the point B takes a new position B dash. That means now there is an angle between AB and AB dash, and that angle, which is represented by phi, is called the angle of shear. So phi is the angle of shear. Okay, or in terms of in mathematically you can represent it as angle B A B dash is equal to phi. So that is evident from the figure. This is B, then B A B dash, you will have this angle phi, and that is the angle of shear. Okay, now what is the implication of third figure? So the implication of third figure is, if you have a cylinder, you cut the cylinder along AB. Okay, so you cut the cylinder along AB, and if you spread that out, you will get the shape of a rectangle. and that is shown here. So ABCD in the third figure represents the rectangle before twist, and AB dash, C dash D, see this is actually C dash, this is C dash. So AB dash C dash D will give you the shape of the parallelogram after twisting. Okay, so you have a cylinder, you cut the cylinder with a scissors along the line AB and then you spread it out, you will get a rectangle, that is ABCD before twisting, and after twisting that rectangle will take the shape of a parallelogram AB dash C dash D. Okay. Now you have one more angle theta that is towards the base. See, you can see theta at this point. Okay, so what is theta? So theta is the angle of twist. Okay, so theta is the angle of twist. So here you have two angles. One is phi, that is angle between AB and AB dash, which is known as the angle of shear, and theta is the angle of twist, that is angle BOB dash. Okay, so let us write that also. Angle BOB dash is theta, that is the angle of twist. Now we have the expression BB dash is equal to, okay, so now you take the second figure. From the second figure we have BB dash. What is BB dash? BB dash is the arc. It's a small arc. So that arc will be equal to angle into radius. Okay, so arc is equal to angle into radius. So what is the radius here? The radius here is OB dash from the second figure into theta. That is the angle. OB dash into theta. Okay. And now from the comparing it to the first figure, you can see that this O dash B is nothing but AB. And corresponding to theta, you have phi. Okay, so first you write BB dash from the second figure, that is OB dash into theta, and then you compare it to the first figure, so it is equal to AB into phi. Now what is OB dash? OB dash is X, as you can see from the second figure. That means you are assuming a cylindrical shell of radius X and thickness dx. Okay, that's the first cylindrical shell which you assume, radius X and thickness dx. So O dash B, OB dash, as evident from the figure, is nothing but X into theta is equal to what is AB? AB is the total length of the cylinder, L into phi. Therefore, you can write angle of shear phi equal to X theta by L. Okay, so now you can write the rigidity modulus. So the rigidity modulus, say N or G, so let us represent it as G, is equal to tangential stress by shearing strain. Okay, so that will be equal to tangential stress. Now what is stress here? Stress is nothing but force per unit area. Okay, so let us write it as force per, now what is the area? So here you have to consider the area of the base of the cylindrical shell. That is from the figure 2, that will give you the base of the cylindrical shell. The area is given by 2 pi x into dx. Okay, so 2 pi x dx will give you the area of the base of the shell. So that force, the applied torsional force divided by 2 pi x dx will give you the tangential stress. Then that divided by, what is the strain here? Strain is nothing but phi, that is the shearing strain, phi. Okay, so this will be equal to F divided by 2 pi x dx phi. Now let us write an expression for force from this equation. So force will be equal to 2 pi x dx phi into g. Okay, now what is the expression for phi? See, you have an expression for phi. Say this is equation number 1. You can mark it as equation number 1. Then phi equal to x theta by L. Therefore, the force becomes, so this will be equal to 2 pi x dx g into x theta by L. So that will be equal to 2 pi g theta by L into x square dx. Okay, so this will be the force acting on that or at the base of the cylinder. Then if you have the force, you can easily write the moment of the force. So next step is the moment of this force, the moment of this force about the axis, about the axis OO dash. OO dash is the axis which we are considering. So the moment of the force about the axis will be equal to this force into perpendicular distance, that is x. Okay, so force into the perpendicular distance x will give you the moment of this force about the axis. And now this is the couple, that is this moment. What is this couple? So that will be equal to 2 pi g theta the whole divided by L into here you have an x dx also. Okay, into x square, you have x, already x square is there, but you are multiplying it with the x, so it will become x cube dx. So this is the couple required to twist the cylindrical shell of radius x and radial thickness dx through an angle theta. Now we have to find out the total moment of the whole cylinder. This is the moment of just one cylindrical shell, and I have mentioned earlier that the cylinder, the total cylinder is composed of a large number of cylindrical shells ranging from radius 0 to r. So if you want to find out the total twisting couple on the cylinder, then you just integrate the last equation, that is say we will number it as equation number 2. So you just integrate the second equation, equation number 2, between the limits 0 and r. Okay, so the next step will be the total twisting couple, the total twisting couple of the cylinder, of the whole cylinder. It will be equal to, you have to integrate the expression between 0 to r. Okay, integral 0 to r 2 pi g theta the whole divided by L into x cube dx. So now let us integrate it. That is equal to 2 pi g theta by L are constants. Integral 0 to r x cube dx, that will be 2 pi g theta by L into, when you integrate x cube, you have x raised to 4 by 4 between limits 0 to r. So that is equal to 2 pi g theta by L into r raised to 4 by 4, or you can write it as pi g theta, or say pi g r raised to 4 by 2L into theta. Equation number 3. So pi g r raised to 4 by 2L into theta will give you the total twisting couple of the cylinder. Okay. Now, the couple required to twist the rod through theta equal to 1 radian. So in equation number 3, you have theta. If you put theta equal to 1, then you will get the twisting couple for twisting the rod through theta equal to 1 radian. And that is called the couple per unit twist. Okay, so that is called the couple required for unit twist. So couple per unit twist is obtained by putting theta equal to 1 radian in equation number 3. So that will be pi g r raised to 4 by 2L. So pi g r raised to 4 by 2L will give you an expression for the couple per unit twist, and it is normally represented as C. Okay, so that is the couple required for twisting the cylinder through unit radian, that is theta equal to 1. So equation number 3 is the required expression for this derivation, that is the twisting couple of a cylinder, and equation number 4 will give you the couple per unit twist. And remember that we have derived this equation for a solid cylinder. That means the cylinder is composed of coaxial cylindrical shells packed very close to each other, and the radius of each shell varies between 0 to r. Now what will be the equation if the cylinder is a hollow one? So hollow one means the one similar to you have seen in figure number 1. Okay, so that is, I haven't shown any coaxial cylindrical shells in that figure, so that can be thought of as a hollow cylinder, which means that the inside portion of the cylinder will be empty. Okay, that means if you take a piece of paper and roll it into a cylinder, you will be able to see that the inside of that cylinder is hollow, and that is what we mean by saying a hollow cylinder. Now, the only change for equation 3 and 4 will be r raised to 4 will get replaced by, it will get replaced by, any idea? R raised to 4 will get replaced by, because if you are having a solid cylinder, you have only one radius, that is R. But if you take the case of a hollow cylinder, then you will have to take two radii, that is the inner radii as well as the outer radius. So inner radius and outer radius you have to take into account, and let me write it for a hollow cylinder. For a hollow cylinder, so this is a case, typical case of solid cylinder, so you have to discuss this also. For a hollow cylinder with inner radius R1 and outer radius R2, the total twisting couple Okay, that is equation number 3. Equation number 3 will get modified as pi g theta by 2l into r2 raised to 4 minus r1 raised to 4. Okay, similarly, the couple per unit twist, that is equation number 4, will get modified as pi g by 2l r2 raised to 4 minus r1 raised to 4. So this will give you the couple per unit twist of a hollow cylinder. So let us give equation numbers. So equation number 5 and equation number 6. Equation number 5 gives the total twisting couple for the hollow cylinder, and equation number 6 gives you the couple per unit twist of the hollow cylinder. So this is the derivation which we were discussing for quite few minutes. That is how to derive an expression for the twisting couple, or this is also known as the torsional couple of a cylinder. So equation number 3 is the main answer to that question, pi g r raised to 4 by 2l into theta, and from that when you put theta equal to 1 you will get the couple required for unit to twist, and that is equation number 4, pi g r raised to 4 by 2l. And then we have discussed the case of a hollow cylinder where the only difference is r raised to 4 is replaced with r2 raised to 4 minus r1 raised to 4, where r2 is the outer radii of the cylinder and r1 is the inner radii of the cylinder. So this question can also be asked as an essay, even though it is not a full-fledged essay, but at times this question can also be asked as an essay. So you have to note down each and every mathematical steps with the explanations I give, so that you will be able to prepare a very good note for your examination point of view.